welcome back my dear students, and this is the last lecture for this project management course. We have tried to cover a lot of topics, but I will try to wrap up GERT. I know it is a little bit theoretical, but we will try to basically give it an example more as a trying to understand problem rather than trying to solve them. But generally the concept which we have used, I am repeating whatever I have said in the last class, and I may have been repeating many of the concepts time and again, but trust me, the concept which we did in PERT, CPM, the crashing, the leveling concepts, the decision trees, all can be extended for the GERT, only that the logic concept is coming in a very big way, such that you can consider the concept, stochastic probability, or the probability that the path would be taken, and the looping concept. So, if you remember, we in the last slide we discussed about the W function and whether in the series and the parallel concept how they can be either added or multiplied depending on what concept which you are trying to follow. And W function was basically probability into e to the power the functional value of time. It is basically something to do with the generating function. If some people are aware of the concept of generating function, moment generating, characteristic functions from the point of view of probability. That is not very important, but I just thought I will mention that. So, the method for obtaining the desired information from equivalent W function will now be discussed. Since the time parameter does not affect the equivalent probability, the equivalent probabilities can be obtained by setting the dummy variable is equal to 0. So, the variable based on which you are trying to calculate that S value, that can be set to 0, and you can differentiate that, put it to 0, that actual differentiation function, and then find out the overall characteristics of that function, not the characteristic function, but characteristics of that function. So, for the two branches which are series, I told you what you do, you just multiply them. Now, if the question is if they are in parallel, what do? You just add them. If the question is now, third question from your point is if three of them are series, what do I do? Multiply W1, W2, W3. If they are in parallel, what do I do? All of them are parallel, just add them up W1, W2, W3. Now, if your fifth question is that if two are parallel and both of them are in series with the third one. So, sorry for that, let me go back to the. So, if consider this, I will consider as 1, this is 2 and this is 3. So, the logical answer is, if you ask a question that how do I find out the W equivalent function, it is very easy. For that first two, 1 and 2, they are in parallel. So, if they are in parallel, what would you do? You will add them. So, it will be basically W1 plus W2, find the equivalent form, and if it is 3, so what you will do? You will basically multiply by 3. So, whatever the complicated structure is, you just follow the concept of for the series one, you multiply, for the parallel one, you sum. So, again continuing the discussion. So, I just went one step forward in order to make you understand. So, but just again tracing back the discussion. For two branches in parallel, the equivalent W function will be the sum of them, and if I want to find out that at the case when the W variable is 0. So, obviously, e to the power whatever value which you have, that is multiplied by t s value which is 0. So, obviously, it will be 1, that is e to the power 0 is 1, and based on that when you find out the W function, it will be P 1 and P 2. So, for the series one it will be multiplication, for the parallel one it will be sum. For the equivalent time, it is seen that by differentiating that equivalent function W which you find out for whatever complicated network which you have, if you differentiate with respect to 0 and some expression will come. For two branches, when you differentiate, the expression which comes is P1, P2 and in bracket T1 plus T2. So, obviously, let me point it out, when you differentiate, the exact value you want to find out would be the case when the equivalent dummy variable is put to 0, and for the two branches in parallel, the function is P1 into P2 plus P2 into P1. For both of these expressions, the division by PA will yield the desired results for the equivalent expected time. The need for the division is due to the fact that the equivalent time is a conditional variable, that is conditioned on the branch being realized. If it is not realized, obviously that value would not be coming. From the above, it is seen that the equivalent expected value would be, for the case when you want to find out the average value, it will be the differentiation, partial differentiation obviously, for the equivalent value WE, where the dummy variable is not 0, and the other value being the WE when the dummy variable is 0, where mu suffix ne is defined as the nth moment. So, it can be the first moment, second moment, third moment, whatever it is. So, if you remember very simple class 11 and 12 algebra or simple arithmetic or the series expansion, what we had x plus a to the power n was basically given by NC0 x to the power, let me write it on its equivalent, n a to the power 0 plus NC1 x to the power n minus 1 a to the power 1 plus dot dot dot, place the last one would be NCn x to the power 0 a to the power n, and that can be done for whatever series expansion you have, depending on what is the domain and the range of x of a and whether n is an integer, whatever it is, and you can basically have different type of expressions. Now, depending, and this why this is important is that when you come to the moment generating function and the characteristic function, basically they will give you the properties of the probability distribution. So, in the similar way, when I take the first moment, second moment, third moment and so on and so forth for the nth moment, and when we expand or put the value for the dummy variable s equal to 0, they would give me the characteristics of the function based on which I want to study what is the average equivalent time and the corresponding probabilities for the network, GERT network. Furthermore, when we put find out the nth moment, so hence this is the moment generating function of the equivalent time, and that time would be given by T suffix e. E is basically the equivalent time. In the similar way, when you have the expected time in the PERT network, it is equivalent at this time to define the nth cumulative, which is kne for any values n less than 3, and which is given by this formula. So, what we need to do is basically try to find out the log of this function. Now, this log of this function would have some implication. I know it is a little bit difficult for people to understand, but there is a concept of maximum likelihood estimation concept, which is very heavily used in statistics. So, we are trying to basically bring some semblance with the concept as you are trying to find out the cumulative values with respect to the maximum likelihood function. So, maximum likelihood function very simply is that you find out the log of the probability function, then differentiate that log of that function with respect to the parameters which you want to find out, and then put that value is equal to 0 and find out the estimated values of this parameter. So, if there are two parameters, you will do partial differentiation twice, considering, and for the first case we will partially differentiate the actual log likelihood function with the first function, consider this is say for example alpha, considering beta is constant. In the second case, we will again differentiate the log likelihood function with respect to beta, considering alpha is constant, and we find out these alpha and beta values, which would be estimated values. So, in the similar way, we can do using that same concept. Thus, the second moment about the mean, the variance. So, second moment is basically to do with the variance, the third moment is to do with the skewness, fourth moment is to do with the kurtosis. So, I am trying to bring a simile to the concept of probability. So, using these equations which hold for all different type of branches, the values of subscript e may be replaced by the subscript of the branch under the consideration, and you can expand this. The W function was developed based only on the series and the parallel network for the loop. Hence, however, it can be shown that any network is a combination of series and parallel equivalent. So, it can be extended to any case. The self loop is a good example. So, if you consider the self loop, so if you have the self loop here, let us consider here,
which I am now highlighting. Let me try to basically use a different color. So, it is yellow now. So, the color has changed. Now, if you consider this self loop, the first part onto the left where I am highlighting, there is a loop. See, this is the loop which I have. On the right hand side, there is no loop. Now, when I do this self looping, it basically means the loop is basically a simple concept of a parallel circuit. So, if it is a parallel circuit, obviously you will have the concept of the probabilities of the time. Use these probabilities and the time with respect to the W function. For the series one, what we did? We basically multiplied the W function. For the parallel one, we added up the W function, differentiated with respect to S, that is the dummy variable, put it to 0 and then found out the values. So, you very simply proceed in this line, find out the equivalent values on the nth moment for a very simple looping circuit, and when you have the looping circuit, you can basically find out the equivalent probabilities and the time as shown here. So, whatever complication which you have, you can simply convert into a series and a parallel depending on what the concepts of the GERT are or the GERT is, and then you can convert them accordingly. For the jth branch, there are j branches equivalent to the feed branch in B in series. This example illustrates the concept that if the W function holds for both the series and the parallel, it will hold for the whole network, and the overall network probabilities and the time can be found out for the whole network as such, corresponding to the fact that each of the arcs have their equivalent W functions, which have been calculated using the concepts of series, which means being multiplication, parallel being addition. So, if you have the chart, so in the first column which you have the network type, that are series, parallel and loops. Loops can be of any complication, parallel can be of any complication, series can be any complication, but given the concept, the formulas which you have is for only A and B, it can be extended to any level, as I mentioned that there in 3 or 4 slides before. The equivalent W functions are given for series, parallel and the loop, and the equivalent moment generating functions are given. So, basically using this concept, if there are, say for example, one series and one parallel, you will basically take A, B, combine them in any concept which is there. If so, say for example, there are two parallel, so you will, if there are put two parallel, you will first use the concept which is given in the second row, which is B element here. Find out the equivalent W function, find out the equivalent moment generating function. Then see if there are two series, then use the concept which is given in the first row, which is with the bullet point A, find out the equivalent moment generating function, find out the equivalent W function. Then check what the relationship of the series and the parallel is. If both of them are parallel, then again you use the parallel concept. If there is a looping, use the looping concept. If they are in series, use the series circuit and proceed accordingly. So, consider the network which is given here. So, basically you have the loopings which is happening. So, let me show you the loopings. So, there is a loop here. So, there is a loop here, there is a loop here, there is a loop here. So, all of them would basically be replaced by the looping concept. Once they are done, these two and this one, these two means this which is 1 and which is 2, they would be combined considering that is series concept. So, this is the series which I bring. So, once you find out the looping one, combine looping 1 with 5. So, I am basically meaning the 1 here and the 5 here, combine with the second and the third and proceed accordingly. So, obviously all other circuits would be termed considering the looping, parallel and the series. So, listing on the looping for the complex network which was just discussed. So, there would be loops, as I mentioned, if you go back to the slide you will understand loops L1, L2, L3, L4, L5, L6, L7. The elements would be loop considering the W functions would be, the first one is W1 into W2 into W3 divided by 1 by WE, which is the equivalent value of W, how you found out. and the last value would be depending on the W values would be W2, W in all these multiplications, W2 into W6 into W12 into W13 into W9 and W5. So, if you can find out those values, they can be calculated, and the non-touching associated loop and the non-touching associated 3 loops can be correspondingly found out. So, what you have done, if you have complicated network loops, you have basically divided them into parts and found out the equivalence of the loops which are numbered from L1 to L7. So, network with multiple inputs and multiple outputs. So, I have just given the diagram such that they give you a very simple concept, the how they are equivalent. So, the equivalent concept can be brought into the picture considering the looping for the series, the parallel, and the concept being series and parallel, whatever combinations which you have, remembering that you have the probability, you have the time, you have the W functions, combine the W functions in whatever concepts which you have, then find out the differentiation, put the W variable 0 and find out the equivalent values, and then find out the probabilities and the time. So, now I will just go into the briefly about Q-GERT and few concept of theory of constraints. So, Q-GERT, which is queuing GERT, is the modification of the traditional GERT approach, in that it recognizes special circumstances where multiple numbers of project teams or activities must be taken into consideration in the same time. So, in the GERT problem, you considered, say for example, only one project, and the activities had loops, activities had probabilistic time, activities had probability that a certain loop would be taken. But to basically make things complicated, now we are trying the queuing GERT, where the combinations of the projects or the activities are being done in such a way they would be intertwined with each other. Reason being that in the concept of GERT, we had looping with respect to the jobs which are there in the project itself, but it may be possible that the jobs are at different projects, but they are interrelated. Consider this: you have a very sophisticated CNC machine, and that sophisticated CNC machine is very costly. You cannot buy a second one, but that has to be utilized for both two different projects. Consider project 1, you are making a very sophisticated machine, say for example for Tata Motors, and the next one another machine you are trying to make is, say for example for a company Reliance. But that CNC machine which you have has to be utilized for both these projects, Reliance and Tata Motors, but they have to be done in such a way that apart from the looping which is there for both for the Reliance and the Tata Motors, they would be intertwined with each other such that the concept of the queuing GERT should be utilized. But the basic concepts of probability time, probability activity happening, the looping would always be there in the Q-GERT. Q-GERT gets its name from special queuing options which is available for modeling situation in which queues build up prior to bringing the activity. So, queues can be a part and parcel of the Q-GERT process, which is not there in the GERT. So, which means that the jobs are being taken up as and when they come, such that the delays of the activities or the time differences which are there are already specified, but in queuing we will consider that the arrival and departures are probabilistic. So, it may be possible some of the jobs have already piled up such that they would have a cascading effect on the succeeding jobs which would basically be there in the whole project or in the conglomeration of the different projects which you have. Further, Q-GERT allows the modeler to assign unique network attributes such like activity time was one important factor in GERT, probability was there, other being nodal branching probabilities. So, if you reach a node, so there would be branching probabilities for going from node 1 to node 2, which would be there in GERT, but it would be more complicated in Q-GERT considering the concept of queuing is also coming into the picture. So, this means that attributes, again I am reading it, activities, activity times, nodal branching probabilities to each individual projects, and then process these projects through a single generalized network such that you are trying to basically bring an equivalent form of all the complicated networks which are there in front of you. So, we will just very briefly go through the concept of theory of constraints and critical chain. So, networking schedule is a powerful technique which is widely used. We have seen that it is simply and handles precedence relationship in a very nice manner, as we saw using the Gantt chart, the PERT, CPM, and further on the GERT. And just briefly in a few minutes I mentioned about the Q-GERT, because trying to consider that would become a subject by itself. So, it is normally used in large projects, but also many smaller projects may benefit from network scheduling problem. A disadvantage is that resource constraints are difficult to handle. If you remember that I did mention time and again that initially for PERT and CPM time is the concept, then we saw that if resources are unlimited then well and good. If they are limited, then obviously the problem would come up that how you will try to handle the concept of resource constraint in the PERT and CPM, and then it can be extended to the GERT and the Q-GERT also. So, Goldratt in 1997 came with the concept of critical chain. So, normally we schedule under the assumption that unlimited resources and then try to adapt this schedule to the resource constraint. So, initially we consider resources are absolutely not a problem, then we schedule it and then try to tackle the problem considering at each and every level they are resource constraints, but Goldratt in 1997 said it was false. Goldratt published a theory in 1997 allowing scheduling taking resource constraints directly into account such that it could be made. This technique is called the concept of critical chain and is based on the theory of constraints, the work which is a part and parcel of operation research and operations management. The theory of constraints was first published by Goldratt in 1985 and basically it came into the force in the 1990s and was quite useful and helpful in trying to solve many of the complex problems. But the problem was that in general the conceptual framework of theory of constraints, critical chain were excellent, but trying to basically bring into the practical sense it was a little bit more complex, but it was very difficult for people to understand. So, he was studying the bottlenecks in the production and claimed that there is always only a few bottlenecks and these bottlenecks limit the total capacity of the overall network. So, say for example, you are trying to do whatever the sequence of the job is, whether there are queues or whether they are not queues, whether time delays are there, leave that. Very simply consider there are three main jobs. One is working on the lathe machine, one is the work on the grinding machine, and one is say for example working on the shaper. Consider very simple machines in the shop floor. Now, consider due to some reason that the time taken in these three machines are T1, T2, T3, all of them are probabilistic irrespective of the fact that the jobs are being done right on time, but consider they are probabilistic. To make life things simple, even though probability is a concept for the practical sense, we make the time as equivalent deterministic time. But now, when we try to basically implement that in a work schedule for the project, it may be found out, say for example, that a grinding work which is a precision work takes a lot of time. So, that would basically be a bottleneck, because all the scheduling things which you are going to do for the subsequent work and all the inventory control which you are going to do, inventory word I am trying to bring it for the first time for this whole project, because resources are an issue and inventory being very high, very low would have a consequence on whether resources are constrained or not. Consider the grinding one is one of the bottlenecks because it takes time. So, we will be more interested in trying to basically schedule the work for the grinding machine in such a way that the work can be done to the maximum possible extent such that the resource allocation for all the three machines, in our case we are considering only three machines, can be done to the maximum possible extent with minimum resources such that the resource constraints along with the bottlenecks are considered at one go. Point 1. Point number 2, you can think that there would be such resource constraint at every level, there would be different type of resources, there would be different type of bottlenecks. So, trying to consider the bottlenecks or trying to basically pinpoint the main bottlenecks would be the best possible way how you tackle it. His approach is to focus on these bottlenecks and see to that they are never drying up. That means, bottlenecks do get the jobs each and every time. To prevent the bottlenecks from drying, he places buffers in the front of the bottlenecks and tries to basically do the work such that the buffers are resource constraints in some way such that the addition of the resources on other work is basically planned accordingly. The bottlenecks also pace the feeding on the products. The bottlenecks are denoted by drums, and based on that we proceed. They pace the speed of the feeding products. From the drum there is a rope to the first operation in the production line. So, the rope would basically mean that what is the linkage which is happening between the bottlenecks and the resources which are put there. In front of the bottlenecks is the buffer preventing it from drying up. So, technically it means that the rope is some sort of linkage which is happening between the buffers such that you can take corrective actions for the bottlenecks. So, this is what I mean. So, there is a rope from the drum, and this light colored one is basically where I am putting the color yellow is the buffer, and this buffer basically has a consequence on the drum and how the feedback happens. Goldnut claims that an hour lost in the bottleneck represents the loss in production, an hour saved in the Norton bottleneck is an illusion, since in any case it will be stopped at the bottleneck. This is the same theory that Goldnut introduced in 1997 for the scheduling projects. So, in many ways I am going a little bit fast in order to basically inculcate you with the interest of what is theory of constraints, and then basically try to wrap up this course. In many ways it resembles network scheduling. His critical chain is the longest theory of resource constraint activities throughout the network, which is very widely utilized. Time and resources are handled in a single pass in any of the concept. So, with this I will try to close this project management course. So, it has been a very good experience from my part, and I am sure the students have learned the concept of what we mean by network flows and network diagrams, then how the different concepts of PERT and CPM can be utilized, how the concept of, say for example, different variables, societal concepts, how it basically makes into the project sense, those are considered, how the different type of decision making tools can be utilized, how the expected value can be utilized, how the variance is an important factor, it can be utilized to at least rank a project, how the different type of financial issues, the IRR, the fixed rate of interest, floating rate of interest, those could be utilized. We found out how the duration concept can be utilized. Then we went into the concept of utility analysis, how the different concept of utility, four different types of utility functions could be utilized. Then how the concept of normality and the concept of utility being quadratic, they make a sense one-to-one correspondence, and what was the reason for that. Then we use simple concept of inequality, Chebyshev inequalities, though briefly, and how can be utilized considering the central limit theorem to be true. Then we went into resource constraint scheduling and how jobs could be scheduled considering resources an issue. Obviously, thinking on the fact that in PERT time was probabilistic, and then we solved a very simple problem in the resource constraint networks PERT concept, and CPM was basically a simple follow up of that. We also considered the four different precedence concept which was there: end to start, start to end, start to start, and the other fourth one. Then we went in the area of GERT and considered how the 6 combinations of 3 inputs and 2 outputs could be accomplished using the concept of series, parallel, and the looping concept. How the probability of time was important, how the probability of a network or the arc being taken was important. And then I gave you a very brief, though we did discuss in some details, and I did mention that the best book would be Pritzker, that how the looping concept can be considered, how the W function can be used for any combination of series, parallel, and the looping one. And then we went to the moment generating concept, and then try to wrap up giving a very brief discussion of the theory of constraint, the concept of this critical chain which has been proposed by Goldnut. With this I will close this course, and you, as I mentioned, that we will have 8 different assignments for 8 different weeks. They would be an end term, and whatever queries are there, as the course progresses, please get in touch with the office, MOOC office NPTEL, and the TAs and myself will try our level best to immediately answer to all the queries. And the readings which I have given, I will strongly suggest my dear friends, my dear students to have a look at the readings and follow these notes or the slides which are giving, not as the end in all concept, but that is just a conglomeration of the different concepts which I have used. And I am sure they will benefit in the long run trying to utilize the concept of project management. With this, I will close this course, and thank you very much for all the attention, and I am sure everybody will do very well in life. All the best. Thank you.